Up if you can. A good idea. Okay, so how are we going to do this? We want to find the lines tangent to and normal to the curve at that point. So what would we do? Derivative. Okay, good. We're going to differentiate implicitly. All right. So what do we get from the first term?
16x.
Plus product rule. Let's leave the 9 out front. How about? And what does the product rule give us for x times y?
X y prime plus y.
Good. Everybody okay with that?
Mm-hmm.
Okay. Question? Okay. Next step. Next term.
12y prime.
Good.
19y.
Okay, and
0.
equals 0. Good. All the rest are just constants, right? Okay, so then we just want to isolate the y prime, so we'll push all 3 of the y prime terms to the left, push the 2 non-y prime terms to the right. Agreed? So what do we get here? 9x y prime plus 12y y prime plus 19y prime equals what? Negative 16x minus 9y. And then we just factor out a y prime and divide the rest away. So then we get y prime equals, well, there's my numerator, right? And my denominator would be just all that stuff with the y primes factored out, right? So 9x plus 12y plus 19. Okay. So there's the derivative.
Plug it in.
Exactly. So we're gonna evaluate the derivative at -1, 0 to find the tangent. The slope, right. Good, the slope of, and really the slope of the tangent line. The slope of the curve, which would be the same thing as the slope of the tangent of the curve.
Yeah.
Okay, so if we do that, we get slope of the tangent line is, when x is 1, all those go to 1. So we'll just make those 1s. And the y's go to 0.
That's -1.
Right, so I'm going to get a -1, you're right. So that's going to make that positive 16, and that's going to become a -9, right? So I get 16 over 10, which is 8/5. So there's the slope of the tangent line. The slope of the normal line would be what?
-5.
Okay, so let's do this one first. If the point is, that's the slope, the point of tangency is there, right? So then we just end up with y equals mx plus b. M is 8/5. So if we plug in, was it -1 and 0? We get 0 equals -8/5 plus b. So what's b? And our answer then would just be y equals 8/5 x plus 8/5, right? That's the tangent line. And then normal line would be the same kind of thing. We'd get 0 equals -5/8 times -1 plus b. So what's b? -5/8. And we get y equals -5/8 x minus 5/8.
So the top is the normal line and
Top's the tangent line.
Top's tangent. Okay.
Yeah, bottom's the normal line.
What's the, in the blue M, is that a J?
That's a perpendicular sign. Okay?
Wait.
The top one's tan.
Yep. Top one's tangent line, bottom one's normal line.
Are they always gonna be like that?
No, just not really.
Wait,
Okay, we good? Yep. All right. Next one. How about this guy?
Yeah, how? Oh, that's what my last question was on the test. But not
Okay.
that exactly.
I mean, similar to it. Yeah, let's look at one like this. Okay, same kind of thing. You want to find normal, tangent and normal lines for this function, but it's a trig function. Okay, so I think you're getting a lot better at differentiating using the chain rule. And that's really what this one takes here, right? So if we know y equals 3 sine pi x minus y, let's calculate the derivative. So what am I going to get for, I get y prime on the left. What am I going to get on the right? What do we get on the right? Olivia, what am I going to get on the right here when I differentiate 3 sine of all this stuff? What's that going to look like? You got to use chain rule, right? So what's the outermost layer of this? Sine. Okay, good. So the derivative of sine is cosine. Good. So I get my 3 as the constant out front. Cosine of something. Right? What's next? Okay, good. Now I've got to peel away the trig function and differentiate the next layer, which gives us the next link in the chain rule, right? So times derivative of pi x is pi. Okay, good. So now what? Okay, we've got to isolate the y primes. Well, I've got 2 y prime terms there, right? So what do I need to probably do? Yeah, now keep in mind here, and this is where I think sometimes people get a little bit, just because it starts to look confusing, people mistakenly do things like maybe try to combine those 2 factors. But this factor is absorbed inside the cosine, isn't it? So this is one inseparable thing, right? And the 3, might as well even lump the 3 with it, right? So I'm really going to take all that stuff and I have to distribute it over that quantity, right? Because wouldn't you agree that 3 cosine pi x minus y, I mean, we can't break that apart. That's just something that's getting multiplied by this difference, right? So this is really, it looks complicated, but it's really nothing more than just the distributive property. So then we end up with, on the right side, I get this whole thing times pi. So I'll put the pi out front, how about, with the 3. So I get 3 pi times the cosine minus 3 times the cosine times the y prime. Right?
You could still put the y prime between the 3 and the...
Yeah, you could. Sure, that's fine. Absolutely. Doesn't matter.
That doesn't make sense. No.
Okay.
So why isn't the y prime
Why isn't it what?
next to the 3?
Oh, it could be. Yeah. Would that be better?
Yeah.
Okay, that makes sense.
Okay, there we go. You like that better?
Yeah.
Okay?
No. It's okay.
Yeah.
I like it better at the end.
Yeah, like
I
very
think
good.
so.
Okay. So, how many terms are up there? Total.
2.
Well, 2 on the right side, then 1 on the left side, so 3 total, right? So we're going to combine the y prime terms on the left side. So that means I have to take this whole thing and add it to that side, right? Okay? So I then get,
Can we just add the y prime to the other side?
say it again?
Can we just move the y prime on the
Yeah, we
left
could.
side, right?
Sure, we could. Same thing, only this way we'd have all positive terms,
Oh, okay.
right? So we end up with y prime plus oops, plus 3 y prime
So then what you do?
times the cosine, right, equals 3 pi times that cosine function. And then all I have to do is just factor out the y prime and divide by what's left, right?
Wouldn't it be a 2y?
Where are you looking?
Like if you just divided the 3 cosine the can, wouldn't it be left with 2y? Would it be y prime plus y prime? Wouldn't it be 2 prime?
Well, okay, but y prime is a common factor of each of these two terms, right? I got a term here and a term here. I can undistribute a y prime, leaving me with, now you tell me, Jolie, what's going to be left on the left side when I factor out the y prime?
1 plus 3 cosine.
Yeah, I get a 1 there, right? And here I get a plus 3 cosine of, whatever that cosine function is. On the other side, I've just got this, right?
Yeah.
And so all I have to do is divide both sides by that factor.
Would that just give you pi?
No, it's not, because on the bottom I've got a 1 plus 3, right? I can't cancel those because this isn't a factor of the denominator. It won't be.
If the one wasn't there, would it be?
Yeah.
Okay.
Yep.
If you moved,
Good.
You kind of lost me a little bit.
no, I don't think you can do what I was thinking, so.
Janelle.
Oh, you kind of lost me a little bit.
Okay, let's go back.
Oh wait, never mind.
You sure?
Kind of.
No, here, stop me.
I got right between the second and the
Those two right there?
Yeah.
Okay, what did we do? We just took these y primes and divided them away from those two terms.
So that way.
In the same way, what if I had this? What if I had x plus 3xy? I could undistribute an x, leaving me with 1
Oh.
plus 3y, right? Okay?
Yes.
So if you moved,
Okay.
that Y prime.
So now do you
That make sense?
Yeah.
Okay?
So that way you can get the Y prime.
Oh shit! Why prime?
Okay, now does everybody see? Yep.
Oh, like question,
Mhm.
how come when we were just, when we were just differentiating in respect to x,
Mhm.
we would get the y prime on the left, but now when we differentiate in terms of y, we like have to make that y prime. Does that make sense?
In other words, why did we get, if I move up here, why did we get that y prime there?
Well, no, like when we differentiated in terms to x,
Mhm.
like when we gave our answer, it would be like y prime equals this,
Mhm.
and then we'd give you our answer for that.
Mhm.
And now when we differentiate in terms of y, you don't give us like a y prime on the left, we like end up differentiating and getting our own y prime. Does that make sense at all?
So why do we get multiple y primes?
Like why don't we have why aren't we given a y prime when we differentiate in terms of y? Does that make sense?
Okay, well, now let's be more specific about it. Now when we differentiate, when we implicitly differentiate here, what are we really doing? We're differentiating with respect to
Y.
x. We're differentiating with respect to x. So the derivative of y with respect to x is a y prime. That really just means dy dx, right?
Yeah.
So how come we didn't get it?
Oh, actually, yeah, never mind.
Okay, does that make sense?
Yeah.
Okay.
Yeah, I knew. Yeah.
Okay, now this is, I don't want to go any further unless because every time you ask a question, I promise you, there are other people that have the same question or are maybe not completely sure about that question.
If we, how we started with the y prime being on the outside before you like moved it in.
Mhm.
Could that be the same for the pi? Like, we could have left it on the outside.
Okay, so listen please. So Jolie, are you talking about like right where?
So like 3 pi, like when we put it into the equation after we had,
Right here, you mean?
yeah, could have gone where the y prime was. And stayed there, so then in our final equation, it would have been 3 cosine.
Okay, no it couldn't, because now everybody look up here. So this, keep in mind that, and the thing that I think sometimes it's hard to kind of get used to as you move into more and more advanced mathematics is that compositions of functions can look just enormously complex, but if there's a bunch of stuff that's been gobbled up by one big outside function, that's one factor, right? So this is really just a cosine of, who cares?
No, I'm talking about the next step.
Right here,
Yeah, that pi.
that pi right there.
Yeah, could it be on the outside of the?
Oh, could it be right there?
Yeah.
Oh,
or
sure.
Behind the one.
Okay, it could, but here's the convention, boys. Here's the convention. When you're writing out an expression in math, you want to put numerical constants first, then you put symbolic constants like pi's, then you put variables, and then you put like trig functions. Okay. So, I mean, that's just an easier way to, it's not, is it something, does it make it wrong if it's the other way? No, they're equivalent, but it's just kind of the convention that we use.
So it's like PEMDAS?
Yeah, well, it's not even like PEM, because PEMDAS, you have to follow that, right?
Yeah.
This just makes it easier so it's predictable. So we know that I wouldn't have to go hunting through this big, long expression. What if I had an expression that was stretched across the whole board? And we'll get some of those. I don't want to have to go hunting through the whole thing to find the constants. I want the constants out front so I know where they are. See what I'm saying? Okay. All right, so then here's, everybody agrees, this is our derivative.
Yes.
Does everybody also understand why I cannot cancel the cosines, for example?
Yeah.
Right? Somebody articulate for me and choose your words very carefully. This is good practice. What is the reason why I cannot cancel the cosines there? Yes, sir.
Because the cosine is not a factor of every factor, it's just a factor of like the 3 cosine pi.
Okay, good, because the cosine is a factor of the numerator, but it is not a factor of the denominator, right? It's not a common factor of the denominator, so therefore I can only cancel common factors of the numerator and denominator.
So
Right.
if the one wasn't there.
So if the one wasn't there, yeah, I'd be fine. I could cancel lots of
And then
stuff.
it would just be pi.
Right. Mm-hmm.
Okay.
Okay, but because the one is being added on the bottom, can't do it.
So if we split it up into 2 separate.
Okay, but you can't. See, here's the other thing that's important to kind of, and this stuff will start to kind of come together and you'll get more intuitive about it. But let me remind you about something. If we have a fraction like, if I have a plus b over c, that's easy to split, right? That's the same thing as saying a over c plus b over c. But if I have a over b plus c, I can't split that easily at all. That's really complicated.
Because if 1/2 A.
Yeah, that's not equal to a over b plus a over c.
Okay.
Okay. Does that make sense?
Yeah.
Okay.
So you just have to go up here and solve it.
Okay, so then the last part of this, then would just be to evaluate this at the point -1, 0, right? It is. Yep. Same thing.
Oh, Mr. Roy, I have one more question.
Yeah.
So if it was like 1 plus 3 pi cosine on top, and then you didn't have the one on bottom, you could make it a 1 plus pi, couldn't you?
No, you couldn't.
Oh, you couldn't?
You couldn't. So the question is, what if I had a 1 plus 3 pi cosine? I can't do that because I don't have a common factor of the top or the bottom to cancel.
Oh, I was saying like, and you took out the 1 plus on the bottom. Would you be able
1
to?
plus was on the top instead of.
Oh, on the bottom. Yeah, then I could. Yeah.
Yeah,
Then okay, but what I would do, what I'd have to write it as, you have to be real careful with this.
The 2
I'd have to write it as 1 over that plus pi.
Yeah, okay.
Does that make sense?
That's what I
Okay.
figured.
You can split it up.
No, let's not have a problem like that.
Okay, so now let's evaluate this. So if I evaluate the derivative at -1, 0, whoops. What do we get? So we get the slope of the tangent is then equal to, now what's going to become of this argument of the trig functions? When I evaluate this at x equals -1 and y equals 0, don't I just get negative pi?
Yeah.
Everybody agree?
Yeah.
So this whole thing is just replaced with a negative pi. And the cosine of negative pi is -1, right? So this whole thing right here, whoops, how is that not right? I ran out of virtual ink. Equals -1. And so I just would get -3 pi over 1 plus -3, right?
Wait, Wait, why where did the cosine go?
Okay, so
Whoa.
when x is -1 and y is 0, the angle is just a negative pi, and the cosine of negative pi is just
Negative what?
-1,
Remember the circle?
right?
Wait. Oh yes. Can't you say -2?
I can, I will, yeah.
Oh, okay.
So,
Because pi times -1 minus 0 is negative pi.
How do you remember that negative pi cosine is what? How do you
Oh,
remember?
goodness.
I'm
God,
sorry.
I'm sorry.
Oh, right there.
I'm sorry.
No, that's good, right there, right? Isn't that negative pi?
Remember that's 1 pi.
Okay.
Oh yeah. Okay. Wait.
so just back.
And cosine is x. Right?
Cosine is x. C before s, x before y. Okay?
So, did you get 1 minus 3 because you multiplied 1 plus 3 times -1?
Yep, 3 times -1 is -3.
Why don't you do 1 times -1 too? You know?
Because the 1 is just by itself. It was 3 times cosine of, right?
Yeah, I gotcha.
And all the cosine is replaced by the -1.
That definitely makes sense.
Okay? So then we get, this is just equal to -3 pi over 2,
No,
3 pi
3
over
pi
two.
or -2. So it'll be positive 3 pi over 2. Right?
That's sure.
That's our slope.
So now shall
We
we
gotta
find
find
the
that
normal?
Okay. What's that?
Should we find the normal now?
Okay, so well that's just the slope of the tangent line. To find the tangent line, if I've got the slope, all I'd have to do is plug in -1 for x, 0 for y, right? To solve for b,
Okay.
right? And then to do the normal line, the slope would just be what? -2 over 3 pi, same drill. Okay, and you guys can do that. That's no big deal. Okay. I'm moving on.
Oh, yeah. Oh,
Okay, here's another one.
oh.
So let me explain this a little bit. This is, I sort of abbreviated this. So we've got some function, call it capital F, which is equal to 3 times x times y cubed. Okay? So the first question, yeah, this is related to rate stuff. So the first question then, it wants us to know, how is f dot related to x dot if y is a constant?
Okay, just
Did-
for pressure, what's the dot mean?
Okay, the dot means the derivative with respect to
Why?
t. So f dot, this is the same thing as saying,
That's d over t.
yeah, df
df over t.
dt, and that would just be dx dt. But we use the dot notation to make it more compact. Okay, this is interesting. This is the kind of thing we can do in physics a lot. When you go on eventually, as you all will, and you get through your calculus sequence in college, and then you go on and study differential equations. This is where you kind of start to be able to look at systems and say, okay, now what's going to happen? Like, let's say I've got some system, like let's say I'm looking at, okay, I'm just going to make something up here. What if we've got, what if we're looking at pressure, volume, temperature kind of thing? So we know that PV equals nRT, equals some constant times time. Pressure times volume, or times temperature. Pressure times volume is equal to some constant times temperature, right? So what's going to happen then if we hold the volume constant? So now imagine this. We've got some, let's say we've got some 1 cubic foot volume up here, right? We hold the volume constant, but we increase the pressure of the gas. What's going to happen to the temperature then?
It will rise.
It's going to rise, isn't it? Because as P increases, V stays the same, the temperature increases, right?
Yeah.
Okay, what's going to happen if we hold the pressure the same, but we, let's see how we can do this here.
This reminds me of chemistry.
Well, it is, right? Anyway, I mean, we can abandon this model, but what I'm just trying to show you is that sometimes it's convenient for us to take a look at what happens in this system if we hold one variable constant and change the other one, right? Okay, that crops up a lot in physics, for example. So let's look at this example, which is completely mathematical, right? This is just abstract and mathematical, but it might as well be a physics problem. So if we want to find out how is the rate of change of f related to the rate of change of x, when y is constant, what kind of calculus would we do then? When I differentiate this function, what am I going to get on the left?
F double dot.
Just f dot, right? I'm differentiating with respect to t equals, now what about over here?
That long one. 3.
Okay, what are the constants in this case?
3.
3
And Y.
and y, right? So then is y cubed a constant?
No.
If
Yeah.
y is a constant, isn't y cubed a constant? Right? I mean, pi is a constant, right?
Yeah.
So pi cubed is just some number, it's a constant. It's not going to ever change, right? So all this stuff, these are all constants, and the only variable is x, right? What do we do with constants when we differentiate?
0.
Move them to the front and leave them alone, right? So we would really just have 3 times y cubed times x dot, right? You see that?
Yeah, but then
And so we'd probably write that as 3x dot y cubed,
but where did the x,
right?
yeah, okay.
Because now, you might be asking yourselves, why did we not use the product rule? Can somebody tell me, why did we not need the product rule there? Yeah, because there's only one variable. The other variable, it's not a variable, it's a constant. Y cubed was a constant. Yeah.
Why didn't we make y cubed 0?
Okay, we could. This is overkill, but we could actually do the product rule here. Let me just show this to you. Don't do this. This is not good. But if I were to treat those both, if I were to accidentally treat those both as variables, right? I would have gotten 3 times x times 3y squared y dot, right?
Yeah.
Plus, well, actually, let's not even do that. I mean, I can even make this a little bit easier. If y is a constant, what's the derivative of y cubed? 0, because the derivative of a constant is always 0, right? So that would have been 3 times the quantity x times 0 plus
X.
y cubed times the x dot, right? Everybody agree?
And
Okay, by the product rule, I just do first times derivative of the second, which was 0, plus second times the derivative of the first. Well, we're differentiating with respect to t, so that x would just be an x dot. So we would have ended up with f dot equals that,
and
right?
and like F dot is the same as saying like Y prime, only F dot is related in time.
Yeah, so it'd be df dt, right. A prime would be a derivative with respect to anything else. A dot we reserve for time because that's what, yeah, and that's usually what we do in a physical system is we want to know changing with time.
So
Yeah.
we use it.
Why is y cubed here?
Y is right here?
Yeah.
Okay, because by the product rule we said first times derivative of the second, the derivative of y cubed is 0, plus second,
Oh.
which is y cubed,
Okay.
times derivative of the first. But do we do that? Heck no, we just do that, right? Yes, Lance?
So when do we know we're supposed to be using dots and not?
Well, you never have to use a dot, but it's just like we use primes to make things look better, right? And it really does make a difference. Trust me, if you get a page full of math, having primes instead of a bunch of quotient forms of derivatives makes a huge difference, right? And so dots gives us one additional piece of information. That tells us that the derivatives are with respect to t.
So that's what the dot, how do we use the dot though?
What do you mean?
Dot is
When
respected
you
in
have,
time
like-
instead of.
Well, like if you're differentiating with respect to time, then
Okay,
you
so
use a
it's
dot.
time,
Yeah.
use a dot.
So we'd say that like dv dx we would call v prime, but dv dt we would call v dot. Okay.
So if there's a T, you gotta use the dot.
Yep. And why did we just introduce this? Why haven't we talked about this earlier? Because we're doing related rates. Now we've been kind of focusing more on the implicit differentiation, but if you think more back to the related rates problems, what are we always differentiating with respect to? Time, right? And so that's why we're starting to get into some actual applied problems. So that's where the dot becomes more useful to us. Okay, so there's our answer for part 1. What about part 2? So what if y, or what if x is constant? What are we gonna get? Let's do
That
it
one
again.
you have to do the product rule, right? Don't you?
We don't need to do, right?
Don't give me the answer.
If x is constant, I just get the 3x out front, and I'm just differentiating the y, right? So I'd get 3x times 3y squared,
3y squared.
y dot, right?
And that's it?
That's it. And so we could simplify that
To 6xy squared.
to 9x.
Oh, 3, 2.
Oh, whoa, I'm confused.
Okay, Delaney, ask a question.
I didn't even write down. Can you explain it again?
Yep. So if we're differentiating now, we're doing this, the part 2, right? Part 2, we're saying how is f dot related to y dot if x is a constant?
Yeah.
If x is a constant, then I can absorb,
X is 0.
yeah, all that stuff right there is considered a constant now, right? And so how do I differentiate a function with a constant out? I just leave the constant out front. I can ignore this because it's all a constant and just differentiate the y cubed by the chain rule.
So, oh, so you got the 3 from the cube, not
Right,
the 3.
right. Yeah, that's because, right, that's from the y cubed. When I get the 3y squared, I could have just combined those right
Wait,
away.
aren't the 3 and the x separated?
Because they're constant.
Because that, the way I wrote this, that was just my constant times what I got from the derivative of y cubed.
So if the 3 was in front of the y, then it'd be the constant, when y was constant, it'd be 3y cubed.
Yeah, in this first one up here, what we really did in part 1 was, at least in our mind, we wrote it this way. We wrote it as f equals 3y cubed times x.
So when something's a constant, we just leave it alone.
Yep. Okay, so there's our answer for part 2. Now for part 3, in a way, it's the easiest to think about because now they're both variables, so we would just use the same old product rule we always used. Yeah. Right?
Can we go with that?
Sure. Okay.
Is this that GB?
Let me rewrite this real quick, and then I'll. So we get 3. Okay. Yes. Haley, which question?
So technically, couldn't you just add the two of them together?
No, you can't. You can't because we treated when you treat x as a constant. I mean, it's okay. I see what you're saying. It is going to give you. Let's. I tell you what. Let's do the work, and then I'll answer your question, and then I think it's easier to see that. I know what you're saying though, but I don't want you to just make that
For number,
conclusion.
Does that work every time though?
What's that?
Does that work every time?
No. Uh-uh.
Is she talking about number 2?
She's saying you could add the results of number 1 and number 2 together, but technically that's not true. It just happens to this time. Yeah. Okay. So now, what about this one? So derivative on the left, we've just got our f dot. On the right, the only constant now is the 3. So let's just leave that out front, and now I've got to do the product rule, right? So I've got first times the derivative of the second. What's the derivative of y cubed with respect to t?
3y
Y dot, right?
Oh, why not?
Okay, plus second, which is y cubed. What's the derivative of x with respect to t?
X dot.
There you go. Okay, so then we just end up with, when all the dust settles here, I get what? 9x y squared y dot plus 3y cubed x dot. Okay.
Where did you get? Oh.
Oh, sure.
Okay.
Yeah.
Okay, last one I wanted to go through.
Wait.
Yep. Okay. Okay. So what about this? Okay, so now we've got a right triangle. The length of the right, or the width we could call it, the width of the right triangle decreases at a rate of 3 centimeters per second. The height y increases at a rate of 4 centimeters per second. When x is 15 centimeters and y is 10 centimeters, find the rate of change of the area. We'll just do that one. If we have time, we'll do the other one, perimeter. Okay. So we need a picture, right? So here's our picture.
Would you mind scooting up the top?
Sure. So that's x and that's y. Okay, and really we're going to summarize all this stuff down here anyway. So now we need, if we're doing related rate stuff, we need a picture, if possible, and we need the snapshot values, right? We want to know at the moment we're interested in, what are the given values and what is the quantity we're trying to find. So what are we given?
Length.
Okay, x is 15, good. I'll just leave the units off, how about? Our units are just centimeters and seconds, probably, right? What else do we know?
Y is 10.
What else do we know?
The triangle decreases at a rate of 3.
Okay, what about the triangle does?
The length of x.
Okay, so the length x, right? So how would I say that then? X dot. X is changing at a rate of -3, right? Because it's decreasing. It's getting smaller, right? Make sense? Okay, and then y dot is
4.
+4. Good. And, okay, so there's all the given stuff, right? Now, what is it that we're trying to find?
Rate of change of the area.
So what would that be? Okay, but how would I, what,
Something with a dot.
okay, like a dot? Right? Okay, so there it is. That's step one. Now step two is we want to come up with a parent equation. So we blur our calculus vision, ignore any dots, and come up with a static equation that relates those quantities. So minus the dots, I've just got areas and x's and y's, right? Well, what's the area of a right triangle?
1/2 x times
Yeah, good. So area equals 1/2 xy, right? There's my parent equation. Okay. So now what do I do to the parent equation if I want to relate the rates of change? Yeah. So now I'm going to implicitly differentiate with respect to time so that I will incorporate the rates into my equation. What I'm doing here is I'm creating a differential equation. That's all that differential equation means, is an equation that has some derivatives in it, at least one derivative in it. So when I differentiate, what am I going to get?
A dot.
A dot equals, that's my constant,
Be like x dot y plus
sure.
Oh, that's backwards.
It's kind of backwards, isn't it? Yeah. We just did, the order is really unimportant for the product rule because they're being added, but that's backwards from the way we normally do it. We normally would have said x y dot plus y x dot, same thing, right?
Oh, okay.
Okay. And so then if we want to, the next step would be to isolate the variable that we want to solve for, which it already is, right? A dot's already isolated, and so we just plug in those numbers and see what we get, right? And so we get A dot equals 1/2 times -3 times
Oh, gotcha.
10 plus
1/2.
4 times 15, and we suppressed the units here, but what would the units have been like for x dot?
Centimeters per second.
And centimeters per second, right? Okay, if we put all the units in, but what should the units of A dot be?
It'd be centimeters squared.
Okay, good, square centimeters per
Second.
second. Yeah, exactly, right? So we know what the units are supposed to work out to be, so we'll just cheat. So then we end up with,
15.
so 60 minus 30 is 30 times 1/2 is 15. Good, so we get 15, what are the units?
Centimeters squared per second.
That's it. So that's, at that instant in time, that snapshot in the film, that is the rate at which the area is changing. It's increasing at a rate of 15 square centimeters every second.
Learn something new every day.
Okay?
Like English every single day. Most kids don't even